Jai Hind students, myself Praveen Kumar, Assistant Professor in AKGEC, Ghaziabad, and today we are going to discuss about the subject BSS, that is Basic of Signaling System, and the subject code is KW303. This is basically the third lecture of the Laplace transform. In our last two lectures, we discussed about what is Laplace transform, inverse Laplace transform, and then some important numericals and some standard Laplace transform pairs. So in today's lecture, we are basically going to discuss about the properties of Laplace transform and then initial and final value theorems. Okay, so let us start the discussion. So as far as the contents of the today's lectures are concerned, firstly we discuss about the properties. So we basically discuss about these properties of Laplace transform. Okay, first property is the linearity property. Second one is time shifting property. Then frequency shifting property. Then we have time reversal. Then time scaling property. Differentiation and integration property of Laplace transform, and multiplication and convolution properties. And basically I am not going to cover the derivation part of these properties. Rather than doing this, I will discuss only the statements of these properties of Laplace transform and then take a simple signal and then we try to correlate the properties of these signal with the help of that signal. Okay, so then at last we discuss about the initial value theorem and final value theorem. So how we can find out the initial values, starting value, or you can say final value of any continuous time signal with the help of Laplace transform. What are the advantages? We will discuss that. Okay, so let us start. So firstly, let us discuss about the linearity property of Laplace transform. So this is the linearity property of Laplace transform. So by default, here we are assuming this pair. Xt Laplace transform is capital XS. Okay, so if Xt Laplace transform is XS and another signal, continuous signal Yt, which is Laplace transformable, then that must be Laplace transform must be capital Ys. And we already discussed the necessary condition that the signal must have finite value. They are bounded signal. They must be bounded signal. Okay, so their magnitude sum in a time limit should not be infinite. That's already seen in the last lectures. Then the linearity property states that if we multiply the first signal with a constant A and the second with a constant B and try to take the Laplace transform of this, then this can be easily find out by finding out the individual these pair knowledge. Just multiply this A with this Xt Laplace transform and this constant B with this. So what is the use of this property? So with the help of this property, if the signal is basically combined of several basic signals, then with the help of this property, we can easily find out the individual basic signal Laplace transform and then apply the concept onto the overall signals. Okay, so this is the linearity property. So second property is time shifting property. So as the name suggests, what will happen if we shift the time of any signal? So we will see here. So here, if you have Xt signal, Laplace transform is Xs, then this time property, shifting property of Laplace transform states that xt minus t naught is equal to e raised to power minus s t naught xs. Okay, so this property is very much important. How it is important? We can see. Suppose you have ut signal. We see in the last lecture also we have ut signal, that is unit step signal, and we know the Laplace transform of this is 1 by s. Okay, so this ut signal we already know. Ut signal is what? Ut signal value is 1. Its magnitude is 1 from 0 to infinite, and it will be 0 from minus infinite to 0. Okay, so if we are applying the time shifting property, then we can easily find out the another signal Laplace transform with the help of this. So if ut Laplace transform is this, then ut minus 5, t minus 5, just wait, ut minus 5, then its Laplace transform will be, so here t naught is minus 5, here this is minus 5. Okay, so now its Laplace transform is e raised to power, this is minus 5, so that is minus 5s upon s. Okay, so with the help of this property we can easily find out the Laplace transform of this. So this is ut minus 5 Laplace transform is e raised to power minus 5s upon s. Okay, so we are going to use this signal by default in the coming property, and then try to see how the Laplace transform property we discuss here in this lecture are important to find out the Laplace transform with the help of less difficulty. Okay, so next property is frequency shifting property of Laplace transform. Again we have taken xt Laplace transform is xs. Then the frequency shifting property states that if we multiply the signal xt with some signal, suppose e raised to power s naught t, means we shift the signal in frequency domain, then its Laplace transform is simply xs minus s naught. So this is frequency shifting property. Again ut Laplace transform is 1 by s. Okay, then e raised to power s naught t ut Laplace transform will be 1 over s minus s naught, or suppose if this is s naught is something just like, so you can say e raised to power s minus s naught. So how to utilize this property? Let's take another example. So e raised to power minus 5t, so its Laplace transform will be according to this property. So ut is 1, we know, so its value is, if it is multiplied with ut or not simply, so one sided, that's doesn't matter, so that comes out to be 1 over s plus 5. Okay, and then simply e raised to power 5t, one sided Laplace transform is 1 over s minus 5. Okay, so you can see s minus 5, this is s minus 5. So you can see that the frequency shifting property is also very important aspect or property or characteristics of Laplace transform, and our difficulty is reduced by several extent if we have the knowledge of this property. So let us discuss about the next property. That is the time reversal property. Time reversal property of Laplace transform. So this is very simple. If xt Laplace transform is xs, then time reversal property simply states that if we reverse the time domain, then the corresponding complex frequency S domain is also changed. So this is very simple. If ut Laplace transform is 1 by s, then u of minus t will be 1 by minus s. Okay. So this is time reversal property. Next is the time scaling property. If we scale the time domain, just like see here, so again we assume xt Laplace transform is xs, then the time scaling property states that x of at Laplace transform will be 1 over a magnitude x s minus, sorry, x s upon a. So again we take the same example. ut Laplace transform is 1 by s. Then if someone asks what is the Laplace transform of u5t, okay, so this is basically time scaling, time scale with 5. Okay, so its Laplace transform will be, so you can directly write if you know the knowledge of this property. So that is age 5 here, 1 over 5. Okay, and that is multiply with this is 5. So 1 over s by, just wait, by 5. Okay, so here no change because ut, so this will remain same. This cut out, otherwise this will remain impacted. So next point is differentiation and integration property. So these two property are very, very important because we know the applications of Laplace transform. This is basically used for the solution of the differential equation in complex frequency S domain rather than solving it into time domain. And why we do so? We do so that the complexity is reduced. So the differentiation property states that if xt Laplace transform is xs, then if we take the differentiation of this signal xt, then its Laplace transform will be s xs minus s x0. What is this x0? This is initial value of this signal xt. Initial value. This is basically initial value. This is basically initial value. Starting value you can see. Initial value. Okay. So the end time differentiation here, if we assume the initial condition 0, so then this comes out to be 0 part. So this is Sn x s, otherwise this will increase in s raised to power n. And the next is the integration property of the Laplace transform. So this property states that if here Laplace transform of xt is xs, then integration of xt dt Laplace transform will be 1 over s x s. Okay, and if we take the n time Laplace, then that is 1 over Sn raised to power n xs. Okay, so this is the differentiation and integration property of Laplace transform. Then multiplication and the convolution property of Laplace transform. So again we assume xt is equal to xs here and yt is equal to ys. Then if we multiply these two, then the multiplication property states that if we multiply these two in time domain, then its Laplace transform is equivalent to convolution in frequency domain 1 over 2 pi j, where j is iota is minus 1 under root. So just remember this point. Xs linearly convolute with ys, and the convolution property states that time multiplication property is this one and the convolution property is this one. Convolution property states that the convolution of the two signal xt and yt in time domain is simply the multiplication in the complex variable s domain. What is s here? We already discussed. S is the complex variable and s is basically sigma plus j omega. Okay, where this sigma is the real part and this omega is the imaginary part, angular frequency you can say, and j is minus 1 under root. Okay, so this is the multiplication and the convolution property of the Laplace transform. So these are some of the properties of the Laplace transform which we will discuss. So the last topic of today's video lecture is about initial and final value theorems. So we already know with the help of by reading this that initial and final value theorems, they are basically some kinds of theorems or some kind of predefined statements, and they are helpful in finding out the initial values or the final values of any given signal. So in our case, the signal is, suppose any continuous signal which is basically summable in a particular time domain. Then how we can take the advantage of the transform we are discussing currently, that is Laplace transform. So here initial and final value theorem statement I am discussing in term of Laplace transform domain. The same may be applied in the other transform domain also, just like Z domain. But there at that domain, Z transform is basically applicable to. In our coming future video lecture, we also discuss about the Z transform. So Z transform is basically the counterpart of the Laplace transform. So that means Laplace transform is applicable to continuous signal, Z transform is applicable to discrete signal. We will see later on when we discuss about the Z transform. So again we discuss initial and final value theorem in Z domain also. So here we discuss about the Laplace transform in today's lecture. So if the Laplace transform of any unknown function xt must be continuous and summable is known, then it is possible to determine the initial and final value of the unknown signal at a time t is equal to 0 plus or t is equal to infinite. T is equal to 0 plus means initial value, okay, and t is equal to infinite means final value. Okay, so this is initial value, because I write down so initial value, and that's before final value. Okay, final value. So firstly, what is the initial value statement? So the statement in Laplace transform for the initial value theorem states that if xt and its first derivative, this is very, very important, xt and its first derivative must be Laplace transformable. It must satisfy the Laplace transform condition. Then only you can apply initial value theorem. Then the initial value theorem states that the initial value of the function is given by this formula. Okay, so you can modify this also. So you can write down xt is equal to, if you find out this value in time domain, then you will take definitely, you know, limit t goes to 0 at t. Okay, in original domain. But if you convert it into Laplace domain, then definitely this theorem is applicable. So limit s goes to infinite s S into XS. X S. So this is same. Okay. So this is initial value theorem. So now the question arises here is that if we can easily find out with the help of this theorem, then why we need this theorem? So the answer for this is that sometimes it is not possible, or it is a little bit difficult to find out the initial value in time domain. Then we can easily take the help of this theorem. In the coming video lectures, we will discuss about the practical uses of this when we discuss the initial and final value theorem numericals. So let us discuss about the last point of the today's video lectures, that is final value theorem. Final value theorem. Okay. So let us discuss about that point. So the final value theorem. If the xt and its first derivative is Laplace transformable, then the final value of the xt is given by this formula. Limit x infinite is equal to limit s goes to 0 sxs. We can write down in expansion form x infinite is equal to limit t is equal to infinite, obviously t is equal to infinite t is equal to infinite ft, and if we write down with the help of this, so that will comes out to be limit h goes to 0 s xs. Okay, so this is final value theorem, and this was our initial value theorem. So here in this case we are finding out, so in this case our t was 0 plus. Okay, so just make correction, we are finding out this value, so this was 0 plus. So 0 plus means initial value of signal and if you write down infinite, so that is final value, final value. Okay, so this is initial value theorem statement, and this is final value theorem statements. So in today's lecture, I try to basically discuss about the properties of Laplace transform by taking into account that how we can implement the I discuss the statement along with the basic examples for the properties of Laplace transform, why they are important, and at last I discuss about the how to find out initial and final value with the help of Laplace transform, that is initial and final value theorem in S domain. Okay, so that's all about for today's lecture, students. Thank you and Jai Hind.